First, a few comments, some questions that people asked me yesterday. So one is, again, why was there a decision to go to consider infinite traces rather than arbitrarily long finite traces? Okay? And the answer is that this is still, in some sense, you could argue about that, and it's not as if things are settled in stone. In fact, there's a lot of research going on what happens if you consider yourself to finite traces. But here is, in a nutshell, why it makes sense to go to infinite traces. So let's take a very simple system where I have a coin, maybe a biased coin, and I toss it infinitely often. What can I say about the outcome? Let's make it easy. It's a fair coin. What can you say about the outcome if you toss a fair coin infinitely often? I'm going to get very bored. But I will do it actually, every coin toss I will do in half the time it took me to do the previous coin toss. But what can I say about the outcome? With probability 1, what will happen? Infinitely many heads, okay, with probability 1. Notice this is a qualitative statement I'm saying now. Probability 1, I would say infinitely many heads, infinitely many tails. Now let's change it to say I'm going to toss the coin finitely many times, but very arbitrarily long, okay? Now in any particular finite trace, if I want to talk about what's happening, I cannot make a qualitative statement. The only thing I can make is a quantitative statement. Well, you tossed it, 100 times or 1,000 times, so we can sit down and calculate what is the probability I will see at least one head. But I cannot make qualitative statement about it. So going to the infinite enables me to go from numerical statements about outcomes to qualitative statements. This is in particular important because very often we don't know the actual probabilities. We have system and we think they behave stochastically, but we don't quite know how they behave. So instead of modeling it precisely using numbers that we don't have, we said let's say that they're non-deterministic, but let's add a requirement that certain things should happen infinitely often because that's the way we choose to kind of model probability. And so there is an advantage here by going to the infinite that you can suddenly turn a numerical quantitative statement about into qualitative statement. Now, as we saw, you pay a price for doing so. So now the question is, this is what happened in life. You want something, you pay a price, now you have to decide, is it worth it? And this is in some conversation that's still taking place. So this is number one. The other comment is, somebody asked me about, and this also came up in Mikolai's talk, about where does this connection between logic and automata, what's the limit of this connection? So one is, again, we don't know yet what is the limit. This is very much still an area of research. But I would say there are kind of two branches of this area, okay? And one branch is the MSO branch, in which you can roughly say that MSO equal finite state. Now you can take this, MSO, we know what it is. Finite state changes its meaning, and that's partly what we've been hearing. But this is, if you just look historically, then first of all, we had this connection. This is late 50s, it's about finite words. And then sometimes after that, it becomes about infinite words. And also mid-60s, it's become about trees. And late 60s, 1969, I think it was Rabin is about infinite trees. And it can also go to a certain type of graph. Bruno Courcelle has written by now uncountably many papers about, all have MSO, I think, in the title, MSO and something, okay? And there are many, many papers on the power of MSO over graphs and what's this finite statement over graphs has become more difficult, but the concept of graph grammar. So this is a very rich line, okay? This is a very long line of research that you can say is still, as we're hearing, is still going on. The other direction you can go from this, you say, look, finite state in some sense is a complexity class. You can now start thinking about finite state. Regular expression is a complexity class, right? These are, if you think of languages, these are languages that we can check acceptance in linear time using constant amount of memory. So now you're thinking, now there is another line, and I would say this is logic and complexity. And this is known also as descriptive complexity. And the celebrated theorem that kind of started this line of direction, which interestingly I don't think was inspired by this connection, somehow idea arose independently, is that this is known as Fagin theorem, sigma 1, which is existential second order logic, not monadic, generally existential second order logic, and that's equal NP. And this is known as Fagin theorem. And again, this gave line to the whole book by Limmerman called Descriptive Complexity Theory. And the idea is that the syntactical resources that you are using to describe a problem have some corresponding complexity theory. Tell you something. The fact that existential quantifier means you can think of existential quantifier as a guess, and that's the non-determinism of NP. And I said this is a very rich line of research. And this has even been generalized into the whole concept of what's called implicitly definable complexity classes. Because the beauty of this definition, if you think what's happening here, to define NP, you need a computational model of Turing machines. You need to talk about, you need a notion of non-determinism, and then polynomial time. And nothing here, it's just, you're just using some kind of a classical logic to do that. So the question is, this concept of implicitly definable complexity, again, there's a whole line of research. So the answer is, on the other hand, there are very natural classes for which I don't know of any. Do you know any logical description of, let's say, context-free languages? Yeah, it's a, yeah, but nothing as natural. To me, this is a beautiful, it's a very elegant theorem, because it follows very naturally. And this is also is a very beautiful theorem. Not all classes have something like that. We don't always have a logical counterpart in a natural way. You can try to come up with some kind of an artificial logic, but it's not natural. And the third comment is that we saw that LTL is equivalent in terms of expressive power to first order logic. But if you remember in the history of LTL, when it was first introduced by Pryor, in the early 50s, it was monadic LTL. Did not have the until. Until is a binary connective or binary operator, but when it was first introduced, there were only the monadic modality, which is next time, eventually, and always. So let's call it monadic LTL. And so you can ask, okay, what happened? What's the classical logic counterpart for the early version of temporal logic? And this is also very well understood. And it turns out, so first it turns out that anything you write on, not in general, but when you write things on a temporal dimension, or discrete temporal dimension with first order logic, you can do it with 3 variables only. And what do I mean by 3 variables? Imagine the syntax only give you X, Y, and Z. That's it. There are no other variables. This is the syntax is defined. Usually we give you an infinite set of variables. Imagine we say var equal X, Y, Z. This is it. Go with it. So it turns out that for LTL you can do with 3 variables. This is equivalent. And what you can do with 2 variables is exactly monadic LTL. So we have a clear understanding of the relationship between them. Okay, so let's go back to where we were. We saw that a major advantage of LTL is instead of having a non-elementary translation to automata, we have an elementary translation. And the most elegant way we know how to do that, use alternation Bushy automata. And so let me just first do, this is something that it takes a while to get used to this beast, you know, it's not, it's a different, you have to kind of think a little differently. So I want to give one concrete example of an alternating automaton. So let's take the following automaton. The alphabet is going to be just 0, 1. And the set of state will have two states. Think of them as master and slave. And you start at master, that's the initial state. Now I need to define row, and the set of accepting states is just master. So now I need to define to you what is row. So row of m and 1 is m. Very simple. You see 1, you just stay m. But row of m and 0 is m and s. What does it mean? It means I stay at m, but I'm forking a new, think of it, I'm forking a new process, and that process is going to be in state s. Okay? So this is, we have implicit parallelism here. Now, row of S0 is S. When S is 0, just stay there. But row of S and 1 equal to. What does that mean? So remember, the transition function gives me Boolean formulas. So true is a particular type, positive Boolean formulas. So true is a particular type of Boolean formula, right? The Boolean formula. Now the Boolean formulas tell us what are the requirements, okay? So when it says M and S, you says from the rest of, you should accept the rest of the word, both from M and from S. So what does true require? True requires nothing. True, it says, this is a constraint. True is a null constraint, right? It's happy. So in some sense, it's like, I don't need to see the rest. From my point of view, we are done. We accept now. So typically, we think that acceptance, you have to run to the end of the word. But, you know, I've heard stories about the job interview, where in the middle of the interview, people say, okay, interview is over. Usually it was because of an early reject, okay? Now, in fact, we could also have, in principle, something that would say some row of some state and some letter would be false. What would that mean? The interview is over. I don't need to see the rest of the word. I already know that I don't like you. So this is a very simple, this is, you know, very, very simple automaton. Now it's automaton on infinite word. That means that an infinite branch must see M infinitely often. Okay? Now, can anybody figure out, can anybody reverse engineer this little automaton and tell me what does it do? What word does it accept? Infinite words. What word does it accept? Okay, your reasoning? Right. When you see a 0, when you see 1, you're happy, right? When you see 0, you're not happy. You're launching another process. You say, now at this point, I'm not satisfied. What do I have to do? I've launched another process, the slave process. The slave process, and when you see 0, it stays at 0. So what will happen if, imagine that we have at some point a tail of only zeros. Then we will launch, in fact, we will launch infinitely many slave processes, and they'll all be stuck at zeros. And whenever you're stuck at 0, you get a branch. All the branches have to visit acceptance infinitely often. So a branch that gets stuck at S will never visit M, and therefore that branch will reject. So the only way you will succeed is that this branch eventually will come to C1 and go through, and therefore it says it forces you to do infinitely many ones, which is exactly what, if I did this, globally future 1, always eventually 1, it said exactly the same thing. It's an infinitely many 1. From any point, there is some point in the future where it will be 1. And in fact, this is really the automaton for this. So at G, when something is true, it must be true now and in the future. So it gives rise to a condition that it must be conjunctive. And in this case, it's either going to be true, which is true now, or I postpone it to the future, which is what the F does. Either it must be true now, or it will be true in the future. So we have a very, very simple, in some sense you can talk about, in some sense, a linear time translation from LTL to alternating automata. And this is partly also been a theme of research along that. When you talk about the connection between logic and automata, one theme of the research was make this translation easy. So if you go back to the original result, Bushy, Elgot, Trachtenbrot, it was a non-elementary translation. That means it was hard work. We want very easy work. We don't like to work hard. So why is there, what does it tell you when there is a non-elementary translation from the logic to the automaton? It tells you it's a big gap. It takes a lot to bridge this gap. Now the logic is a given. So how can we narrow the gap here? Make the automata more powerful. So let's make the automata more powerful to narrow the gap between logic and automata. Now, of course, we pay a price when we make the automata model more powerful. What's the price we pay? Something else becomes more difficult. What becomes more difficult if you make the automaton more powerful? The emptiness problem. Imagine I made it a Turing machine, okay? And then the emptiness problem become undecidable. And so there is kind of by now we kind of have a general structure. What should you do if you have some logic? Try to, if there is a big gap between that logic and the automaton model, try to consider a richer automaton model, but find a way to reduce that more expressive model to a less expressive model. So the direction, so we had, in fact, when things started, the initial translation was from LTL to immediately to non-deterministic Bushy automaton, which, by the way, typically, in fact, we do use this, and the W means words, because one of the things we have not discussed is what happened, but we will hear more. What happened when you go on trees? You have automaton on trees, automaton on other things. So typically, this is a notation that was introduced to say this automaton on words. So that was the first translation, and that is an exponential translation. If it's exponential translation, it means we have to sweat it out. If you go back to the early paper, you see it's a difficult, bless you, it's a difficult translation. So we said, well, let's do it in stages. Let's go from LTL to ABW, this alternation Bushy automaton on words. But this result will not be useful unless I came up with another translation, because we this is too expressive. It's difficult directly to test for non-emptiness. So instead we said, okay, let's go from ABW to NBW. This is exponential, but it's actually, you can argue if it's anyway exponential, why not pay the price here? Because this is now a cleaner model. Now we're just about states, and how do we do some kind of a subset construction, and I don't know that I'll have time to do it because I want to cover one more topic of synthesis. But there is a kind of a subset construction that's some modification of the classical subset construction that does it here. And this you can think now, this is a built-in subroutine. You have a library to do these kind of things. People discovered there is another advantage of doing this translation in 2 steps. There are one of the things we want to get is a smaller automaton here. So by now there's a history of at least 20 years of building tools that translate LTL to automata, and they try to be linear and meaner and whatever. And one strategy was to say, look, this object is smaller. Let's do the translation. Let's try to do some optimization here, because this is a simpler object, and this will save us, because the exponential blow up here, minimizing here will save us a lot when we do this translation. Okay? But generally, the idea is to do it in stages, means that each stage is more manageable rather than do it in one big step. Okay, so what this gives us, in a nutshell, we have I can summarize what we call the automata-theoretic approach to linear time model checking in a few lines, right? So LTL is translated into ABW. And then ABW we translate to NBW. And then if I want to check that the formula is one of the basic check, if I want to check formula is satisfiable, then I have to check that it's just emptiness problem. I have to check that this is non-empty. This is satisfiability. And then this was model checking. Another point. So remember that I said when you do model checking, you have to complement the specification. So nominally, I told you that to go from LTL to an automaton is going to be an exponential blowup in the worst case. We can write formulas that we know will have exponential blowup. This is really, you can do better than exponential. And to complement an automaton, anybody remember what was the complexity of complementing? Another exponential blowup, 2 to the n log n. So on the face of it, what does it imply? On the face of it, it looks like doubly exponential. But remember I told you, logic has one beautiful advantage. How hard it is to complement logic? One symbol. So that means that if I build a phi and I complement it, what I will get is exactly a of dot phi. So that means that once I'm in the logic level, complementation is for free. And that's one big advantage of dealing with logic. I don't have to do this hard, bushy complementation. All I have to do is negate the formula and then apply this translation. So that's what we do here. We'll take the transducer, cross A sub naught phi, and we will check for emptiness. This is model checking. So this is it. This is the summary of kind of the basic linear time reasoning using automata. We can do satisfiability, you can do model checking. The key is the translation from logic to automata. Now, the interesting thing is when you go to the early model checking papers, which are from the early 80s, the first papers were not about model checking. They were about something which was more ambitious, which was synthesis. And the idea in synthesis was so we're trying to build a system, and we interviewed the users, and we wrote down, first of all, maybe in English, what is the user wants to do, and then somebody sat down and translated from the English to temporal logic. In fact, people even build tools that do natural language processing and try to go automatically from semi-formal requirement in some usually structured English, they call it, not full free flow English, but structured natural language, to go to temporal logic. And so let's assume that we have obtained some temporal formula, and these are really the specifications. I will come back to discuss this scenario, how realistic is this scenario, but this is people thought we can take. And in some cases, you know, if you go and look at, people have done it. They take, for example, on these machines, you know, between the processor and the memory, the communication is on a bus, and the bus has to be INRSI standard. So Intel published the specification of how the bus is supposed to behave. And people have taken the bus and showed that all these properties can be formalized in temporal logic. They're temporal properties typically. You get this packet, this will happen. You get this packet, this will happen. Packet is lost, this will happen, things like that. So the idea was, this has all been specified to us. We know exactly what the program is supposed to do. And it's completely formal at this point. Why do we have to sit down now and manually write a program? Why can't we just take this specification, think of it as a very high-level program, and just compile it to a program? That's what we do today. We write in a high-level language, and it's compiled to low-level language. Why do we have here to look at this and manually sit down and write the code and then do model checking and discover that we made an error? Why don't we just go directly from phi to some t sub phi? And what do we want from t sub phi? What should be the condition? It should satisfy the specification, right? And this means that the language of t sub phi should be contained in models of phi. And if we could do that, then this is we just have what we have done is we have lifted the level of abstraction of programming, and in particular we have went all the way to declarative programming. The idea of declarative programming is that we should just tell the machine what is it that we want to have, the what. Leave the how. Somebody else should figure out the how. Okay? I mean, this is when if you have children, they come and they ask, I want X. They don't tell you, you should do so and so and so, so I will have X. They just say, I want something. Now it's your problem. Figure it out, right? And in fact, very often, a graduate student come and ask me something, and I said, figure it out. I tell someone, you need to do the following. He said, how? I said, figure it out, okay? I just tell you what I want to see happening. Figure it out the how. That's what we really would like to do. And this is called declarative programming. And this is part of the quest. You know, I told you this kind of funny stories about von Neumann, but people realize early on that programming is actually hard. And it's hard and it's expensive. And we are moderately good at it, but there is a kind of conventional wisdom is a programmer writes 20 lines per day, regardless of the language. If it's in assembler, then you write 20 assembler instructions. It's a functional language, then you write 20 lines in a functional language. And so one way to increase productivity is to raise the level of abstraction. And this, we've been doing it now for starting really from 70 years we've been doing it essentially. Right? Beginning we wrote in binary, then the first big jump in productivity was going to octal, and we've been going up since then. So this will be and the idea in particular of using logic, that goes to the late 60s. People start thinking about it. Can we go from specification to programs? And at the beginning, when they were thinking about input-output programs. So what is it? In input-output program, there is some relation X between X, the input and output. There is some relation. There will be some relation. Y should be the square root of X, for example. And maybe there is also a precondition. If I want to extract square root, the precondition would be X has to be non-negative. So the relation would have to be pre of X implies, this we can call post condition. And now you want to say, well, I should be able to do it. You want this condition, right? For all X, there exists some Y such that pre of X imply post of XY. And if this is true, then first of all, it means that the thing you want to do is realizable. It is true. In fact, for every X, there exists such a Y. And so the early ideas in synthesis would say, if you have a proof, the proof someone should tell you also how to do that. You should be able to extract the program from the proof. And this is not always true when you do classical proof, because as you may know, classical proof can be sometimes what? Non-constructive, right? So there are existence proof that are kind of weird. They say something exists, but I'm not going to tell you what is that object. I just want to prove. And there are such proof in classical mathematics. Yes, right. And this became, in fact, about 100 and, not 100 years ago. About 90 years ago, something like that. It became a huge controversy in mathematics. Is it legitimate to have existence proof that are non-constructive? This became a huge fight in the 1920s and first part of the 30s, mostly between two mathematicians, Hilbert and Bravер, whether this is legitimate. Is it legitimate mathematics to have this weird existence proof that are non-constructive? And one outcome of it was that people said, let's develop constructive logics, intuitionism and even more. And so even today, there are people in computer science and that in logic that said, if this is a constructive proof, then you should be able to extract a program from this. Now, in the early 80s, so remember, the initial thought about what we call formal method was all about a program takes input, produces output. And then in the mid-70s, people start thinking doesn't describe how we use computer. It's about an interaction. So in the early 80s, people start thinking, what would it mean? What would synthesis would mean for ongoing programs? And the first thought was this. We have just developed a translation. We have shown how to go from a formula phi to some machine model. It's a finite set machine. Didn't we, went from phi, didn't we just synthesize a program? Should we not think of this as synthesis? And people say, wow, for the same price, we also have synthesis. Once you can translate logic to automata, you have synthesized a program. And in fact, the model checking paper by Clark, Emerson, and Sisler was essentially this idea of using satisfiability as a synthesis procedure for a different logic. That I'm kind of skipping the whole thing about branching time logic, but this was the idea. And so let's see a little example. So imagine that I'm trying to specify some kind of a print manager. So print manager gets requests, gets jobs, and has to print them. So let's write down formal requirements. What do we want to see happening? So one is that always it is not the case that you print the two jobs at the same time, because this will mess up everything, right? The jobs have to be separated. And the second thing is that always, if you make a request, I'll just write generically GI, if a job is submitted, then eventually it will be printed. And you can say this is it. I've specified a print server. Now, is it satisfiable? It's actually very, very easy to satisfy it, and I'll describe to you now a model. Here is a model. It's a one-state model. And this model, everything is false. J1 is false, J2 is false, P1 is false, P2 is false. Now let's see if it satisfies the formulas, right? There is a trace. The trace is just go through this infinitely often. Yeah, you never print two jobs at the same time. And whenever a job is submitted, yes, eventually we print it. Yes, because no job is ever submitted. So is this a good print server? Not really, right? It's obvious. So what went wrong? What went wrong here? Why? You know, we followed. We used the formula. We built an automaton. We checked on emptiness. We found a witness. What's wrong? There was a property of transducers that I told you about. What was the property? I said transducer have a special property. Receptive. They can't say, I'm not in the mood. Right? They get input, they have to respond. And that means in transducer, we see an explicit distinction in the transducer between input symbols and output symbols. And the transducer had no control over the input, only control over the output. Right? This is I don't know, maybe Buddhism or something like that says, well, you know, as you deal with the world, you should remember the only thing over which you have control are your own actions. That's it. So transducers behave very ethically. They just control their own action and they have to be receptive for anything. Otherwise, they'll never reach nirvana. So that means in the formula here, we lost the distinction. We should have a distinction here between input and output. What are the input variables here? J. Somebody requests a job, somebody sends us a request. It's not under our control. What's the output? P. I'm the controller. This is from my point of view. Somebody else have a different perspective. From my perspective, right, I'm the center of the universe. The sun revolves around me, right? The sun rays are the input, and my actions are the output. And so we have to have receptiveness, and we didn't have receptiveness. So just doing satisfiability, when you do satisfiability, we lose the distinction between input and output. So satisfiability is the wrong approach. And instead, the people realize that what we need to consider instead is a game. Okay? And we see games are very, very powerful construct, and they come up again and again. In particular, remember, the way we got into alternation by starting to think that even temporal formula, the evaluation of a temporal formula can be considered as a game. Okay? This was kind of an internal game, so to speak. This is in some a real game between some environment and a system in which we have input variables and output variables. And at any moment in time, I'm sorry, beta. So I want alpha I always to be a truth assignment to the input variables, and beta I should be a truth assignment to the output variables. And in between them, this is a full truth assignment to all the variables, right? And so this is a trace, and the trace should satisfy phi. That's the way to think about it. You have no control over the input. Now we can, there are various refinements. Exactly how does it happen? Do you see alpha 0 before you respond with beta 0? Or is it, and this is called turn-based game? Or I think in game theory these are called Stackelberg games. Or is it the case that at each moment everybody has to move? And you don't see, that means the system does not see alpha 0 until the second point in time. These are variations of this, and I won't get too much into these variations, okay? And these are called concurrent games. And there are various things, you can look at other things to do that. And so this become known as now as LTL games. Now the history is that these kind of games, they go back that that model of that synthesis questions, again, everything goes back to this very influential paper by Alonso Church in 1957, in which he basically described a model and he raised questions. He didn't solve anything. There are no results in the paper other than here is a model, here are some interesting questions about the model. And one question was, now what was the temporal logic at the time? MSO. So his temporal logic was MSO. But he asked essentially two questions about MSO. The first question was satisfiability, and that was solved by Bushi in 1960. And satisfiability, all you have to do is translate from MSO to automaton, to automata, and then check for non-emptiness. But the other question was, what happens if you look at now as a game? And now we want to know two things. One is there, first of all, what does it mean to build a system? You have the system has to have a winning strategy. What is a winning strategy here? Yes. Yes. You know, it kind of pops into consciousness around this year. 57 must have been something in the air, in the water, right? Because you have Trachtenbrot in Novosibirsk coming with MSO, and you have Bushian Elgot. And I don't quite know the sequence exactly. That's an interesting question. Who was the first one that said, let's look at MSO? Okay, but it somehow the idea pops up independently. The question was church independent of Bushian Elgot, or was it inspired by Bushian Elgot? That I don't quite know. I mean, somehow all things to come at the same time. I don't know, they had some logic meeting in which somebody said, what about MSO? And everybody went home and started thinking about MSO. But MSO kind of pops as a logic in that context. Of course, monadic logic goes back to 1915, okay? But the monadic logic in the context of satisfiability, looking at everything monadic. But monadic logic over structures, where you have an underlying vocabulary, but you're limiting second-order logic, kind of shows up around this period. And it's you're asking a good question. I don't know what happened, what triggered, why is everybody starting to do MSO at that point? Yeah, good.
I guess it's very natural, right? Because people looked at, let's say, first-order logic on structures, right? You know, so Starsky's theorem over the, arithmetic over the rails. There was Pressburger, and they knew by then that second-order logic was undecidable even over the integers because you can easily encode. I mean, they already had Turing, which was so MSO, and what about this?
No, I don't. My guess it would be different. Not as a restriction of second-order logic. My guess is that these people started with this concept of finite-state recognition that came up around came up really in some sense. Say it started in Turing in 1950, but then Kleene and Kleene theorem is I think in 1955. And then I think my guess is people says, what logic can we do? What logic? This is funny notion, regular expression, automata. Is there a logic to it? And they realized that you need to say there exists something about the states, and the states correspond to monadic predicates. This is my guess. Did not come down from the logic. I think they came up from, but I'm guessing. I don't know exactly how the evolution of ideas. These are all interesting questions.
Yeah. I know you will laugh, but there could be a Tarski connection.
There could be a? Could be, yeah. What do you think is a Tarski connection?
The reason, I think I was reading yesterday a review, I have to check it, of the Buchy paper by McNaughton, back in '62 or something.
Yeah.
And I think he wrote something like solving a problem by Tarski or something like this.
Let's follow up on that. It would be very interesting. Yeah, very interesting. So there is a game, and we say, what does it mean to have a winning strategy in the game? So this is a concept. What is the concept of winning strategy? So much of what you see in game theory is what we look at game and we call it an extensive normal form, in the matrix form, right? So you basically says, well, it's a game, you choose some kind of an action, and then you see the matrix and you see the payoffs. But these are games where it's important for us to know what it's an infinite game, it's an infinite Terence game, and it's important what happens in every stage. And the important thing is that at any given point, you see only the history until that point. So if we want this to be really correspond to behavior, in fact, people call it behavioral strategy. What is a behavioral strategy? Behavioral strategy is going to be, let's say, for the system, it will be a function. Strategy sigma will be a function from 2 to the I star into 2 to the O. And it says, based on all the inputs I've seen so far, this is my output. So for example, at time 0, I have seen nothing, but I still have to make some decision. And at time 1, I have seen this one. Each time I've seen everything so far. And I know what I have done. So I only should depend on what you have done. So this is a strategy. Okay? And a particular play, when we talked about a game, and the play is one particular way the game evolves. In this particular, we said that this play is consistent with the strategy. So if this is a play P, then P conforms to sigma if, what do we want? We want beta I to be equal to sigma of alpha 0 through alpha I minus 1. So you behave according to the strategy. And the strategy is winning if P satisfies phi whenever P conforms to sigma. That makes sigma a winning strategy. So this is a game that, from a game theoretic point of view, very often we look at the matrix and things like that. Here, the payoff is just either 0 or 1. Right? You either satisfy phi or you don't satisfy phi. But we are interested overall in not just in strategy, but in a behavioral strategy. So this concept really goes back to the late 50s. But the algorithmic question was not solved. Remember, in 1960, Bushi came up with the automaton description. But it became clear that that does not lead immediately to solving the realizability. Realizability is asking, is there a winning strategy? Synthesis is generating a winning strategy. Now, to try to do this, to kind of develop the line of work, how we arrive at a solution for this, I want to start doing it, first of all, on finite words, because I think that will be much clearer if we do it on finite words. And let's just imagine now that, let's get away from the logic here. We know that the logic is equivalent, all this logic equivalent to automata. So suppose we are giving a DFA, and the alphabet is partitioned into input and output alphabet. Okay? If you want sigma cross delta. S, S0, rho, and F. This is just a DFA. And rho is a function from S cross sigma cross delta to S. And think of this as input, and this is the output. And now we can think of the game. In the game, at every round, again, let's make it simple. Let's make it a concurrent game. At every round, system chooses a letter from sigma, and environment chooses a letter, system chooses from delta, environment chooses from sigma. And so we play this game. We have this A0, B0, A1, B1. And the goal of the system is we want to end up with a word that is accepted. This is how, so you have to choose. Whenever you choose a letter, you see all the letters have been written so far, and you have a winning strategy if you can make sure that ultimately the automaton will accept. So typically we think of a game, we have some kind of a game tree, right? You have some initial state, and there are possible transitions. And this is, maybe think about, this is what we call OR. One player chooses some transitions, and maybe the other player, this is the adversary, so we have AND and OR. And then at the end we have the leaves, and we know whether every point at the end we know whether it's winning or losing. So there is, in fact, a fundamental question that comes, and this has to do with, is the game, given the game, is the game determined? What does it mean for the game to be determined? One of the players we should know that one of the players always has a winning strategy. This is not always the case. Okay, so take the game of rock, scissors, paper. Rock, paper, scissors. I don't know what's there. Rock, scissors, paper. Who has a winning strategy? You have a winning strategy? What's your winning strategy? Kick them in the balls? So this is an example of a game, and if you want, there is a simpler one, which is called matching pennies, which you take a penny and you show it up or down, and I win if they are matching, and you win otherwise. And this is an example of a game that, there's no winning strategy here. There's no Nash equilibrium as long as they're dealing with pure strategies. So on the other hand, there are some games, if you look at a finite game, then we should know whether or not the first player has a winning strategy. And how do you do that? This has to do a little bit what we saw example. We know at the leaf exactly what happens, right? So we can put 0, 1 in every leaf, and 0 will tell us 0 is I lose, 1 is I win. And then if it's a conjunction, I know how to evaluate it. In this junction, I evaluate it. So all I have to do is I have to evaluate it bottom up. And this is just an AND OR tree where you have 0, 1 in the leaves. I will get here 0, 1. So in fact, this is I'm trying to think who is I think it's maybe Zermelo. Was it Zermelo? I can remember right that all final games are determined. I think it was Zermelo. This is to say, if the game is described by a finite tree, and you know exactly what happens at the leaves, now you just do backward induction. And this becomes actually how to do this efficiently on large trees. This is a major theme in AI. A lot of people in AI doing games, and you say, how do you evaluate such AND OR trees when they're very large efficiently? It becomes more complicated if we go to infinite game. But for finite game, this is very simple. So what we should do the same kind of thing here. We should just do backward induction here. So let's compute the winning sets. How do I win without making any move? Okay. If I'm already in a winning position, right? So W0 is going to be F. Okay? So gradually I'm computing how do I win in more and more moves. And then what would be Wi plus 1? Wi plus 1 would be all the states S such that there exists a letter A in delta, such that for all letters B in sigma, rho of S and the pair AB is what? Belongs to Wi. Now, actually, the way I should do it is Wi plus 1 equal Wi union V. Right? I accumulate more and more states from which I know I can win in at most I plus 1 moves. Because I have from Wi I win in less than move in at most. So this is now an increasing set. And the state space is finite. So we know that at some point we will converge. There is a convergence, and we can call the convergence, we call it W infinity. But W infinity is misleading. You reach the infinite number of states. And now I need to know, do I have a winning strategy in the game? So I have one more step to do, which is check is S0, is it in W infinity? And if it is in W infinity, it means that from the initial state, I have a winning strategy. Okay? This answered the realizability question. I done that, I said, okay, I have a winning strategy. Where is the winning strategy? Well, the answer is it's hidden, but in some sense, it is here, right? Because I found whenever I added a state S, whenever I declare S to be an accepting state, it was always, I had a witness for that state, okay? And the witness, let's call it here A sub S. There is a particular, I found one, maybe more than one, but I found at least one, there is some input, some output S, such that I know that from this output, whatever the environment will do, I will go to Wi. And that means now that there is a function here. There is a function, and this function is go from S there's a function from S to delta, and the function is sigma of S is A sub S. And this is a function of states in the automaton. Now, remember, when I defined strategy, I said the strategy was a strategy that depends only on the inputs. So this is not quite, doesn't quite seem to have the right syntax here. But I claim that it does. Why? So let's just simply see. Let's define our transducer that will implement the winning strategy. This is a transducer. What are the inputs to this transducer? Sigma. What are the output? Delta. What is the state space? S. What is the initial state? S. And I need an output, I need I will simply copy the transition function, but not quite, because the transition function there was a function on both input and output. And here I have to have a function that depends only on the input. So let's leave this for a minute. But we know what the output should be, right? The output function should be sigma. The function takes you from S to A sub S. And now it means I can take rho prime and rho prime of state S and an input input A. Actually, A sub S was a bad term because it should be B's. I use B's, so A B sub S. B sub S. I'm missing. I needed to have both input and output. So this should be function from S, and here I would have, A. And what should be we know what the output is going to be here. The output is going to be B sub S. Because I decide what the output is, right? It's under my control, and it's now controlled by sigma, and sigma gives us B sub S at the state S. So this is it. This is now a transducer that implements the strategy. How many states does this transducer have? The number of states. In fact, it is the state space of the transducer is exactly the state space of the automaton that specifies the system. So one of the theorems that we just proved here, actually it was very easy. This is something important, right? In a DFA game, if there is a winning strategy, then there is a finite state winning strategy. This is very nice that we have finite state winning strategies, because if we have an infinite state winning strategy, let's suppose it has to remember all the history, and I'm trying to run it on my machine, at some point I will run out of memory. So finite state strategies are ultimately any kind of protocol that you want to run on a system without incurring somehow slowing down and just grinding to a halt has to be finite state. So we got here that if you're playing DFA games, then in fact we see that the finite state strategy is using really the same state space. All we have to do is to choose cleverly the output will depend only on the set of the automaton. These are called DFA games. And now, let's see how we can perhaps generalize it. And we will generalize it by saying, well, let's make it an NFA. So now, imagine you are given an NFA, and again, you're playing, there is a game between the system and the environment, and to win, you have to end up with a finite word that is accepted by the NFA. There was nothing in the definition of the game, the winning condition, that depended on the automaton being deterministic. It just has the automaton recognize a set of words. Now, I would like to be able to do something similar, some kind of induction, some kind of analysis of the state space to analyze from which states I'm accepting, from which states I'm not accepting. And here I run into a very, very important gap between non-deterministic automata and games. So remember I told you, I think yesterday, the automaton is a very simplistic object. It does not have long-term plans. It does not have any vision. It's in a state. It receives an input. It goes to another state. This is not quite true for non-deterministic automata. Because non-deterministic automaton choose the best runs. And it's the best run for this word. And you should really think about it. The automaton comes in. It first looks at the whole word. And then it decides how to make transitions, because the transition depends on the word. It's not a local transition. Because I'm saying there exists a run. And in particular, if we go to the deterministic Bushy automaton, the automaton first look at the word from here till kingdom come. And it sees the whole thing. And then it makes these local transitions. This is very different than we're looking at strategic behavior. The basic principle of strategic behavior should be you can only act on the information you have. The information you have are the moves that you have seen so far. So if we try to do something like this on an NFA, it will be just simply wrong. Because NFA has what we call clairvoyance. It knows what's going to come. And the strategy, it makes no sense for it. The print server does not know what request it's going to get. So we says, no problem. Why is it no problem? Because we know you can translate from NFA to DFA. So if we have an NFA, we will wave our magic wand and make it a DFA. And of course, we will get a blow up in the state space, but we'll be deterministic, and we will be able to solve the game. So we just reduce it to the problem we have solved before that. Okay? So when it comes to finite games, everything is fine. We know how to do that. Algorithms are simple. Of course, there is a question of implementation. The implementation will depend how big is this automaton. And it turns out that very often this is the big challenging part is to construct the automaton, because we usually start from some logical specification. So the challenge is to construct the automaton. Once you construct the automaton, doing the analysis, it's a simple fixed point calculation. It's not very difficult. But this, in some sense, is kind of warm up, because I argue we should be able to reason about infinite words. And we talked about LTL games. And now we are facing the following problem, right? We would like to play, first of all, one challenge would be that we want this to be on infinite words. So let's try to do infinite words, but let's try to do something simple. Let's assume that we're dealing with infinite words, but there's no acceptance condition. What I mean by that is the acceptance condition is there should exist an infinite run. The automaton should never get stuck. So there is a slight variation when we talk about deterministic automata. Do they have a unique transition, or do they have at most one transition? So let me just modify this here to say that rho is a function, I'm sorry, it's this way. Rho is a function from S cross sigma cross delta. And now I think we do this symbol to S. And this is partial function. So it may be undefined. And so now my acceptance condition is there exists an infinite run, which means that you can never get stuck. You can never be in a state where there's no transition. And these are also called safety automata. So when there's no transition, it means something bad is going to happen. You should never do that. Okay? Don't walk across the ledge. You're going to fall down. Okay? These are disallowed transitions. So now we can talk about infinite games. And how do we solve infinite games? So actually, it's kind of almost the same to solve infinite games. Except that in this game, it's hard to win because it's an infinite game. But it's very easy to lose. Okay? Let's talk about state that we are losing. What is L sub 0? How do you lose in a state? Well, if you cannot make any transition, right? So L sub 0 are going to be all the state S such that there does not exist some letter B, such as for all A, for all, this is B in delta, such as for all A in sigma, rho of S and AB is well defined. So you're in a state S, and there's no one state B that you can do, one letter B, such that you're guaranteed that you're not going to fall off the cliff. So these are states that you're losing, right? This is a losing state. And now I do the backward induction, if you want, on the losing state. And again, it will converge, and all the other states will be winning states. And if you want to look at differently, then I will use this. I will say this is W0. These are all the states that I can make a move. And then, instead of being union, I'll say Wi plus 1 is going to be Wi intersection. And I will repeat the same condition. You can make at least one move. And I will end up with all the states that it's a set of safe states. If I stay within this set, then I'm guaranteed that I never fall off the cliff. And this way, I will make sure that I can solve it, and I get a strategy, and I will never fall off the cliff. So this is for automata, they have no acceptance condition. But what happens when we get LTL? LTL gives us Bushy automaton. So we have two problems here. One, they're non-deterministic, and we saw this gap between non-determinism and strategic behavior. And on top of it, I have to deal with acceptance condition. So it became clear now we are in the mid-60s, and people are working what was known then as Church's problem, which maybe we should now rename it to Tarski's problem. But at the time, people think of it, this is Church's problem. There was not LTL, there was MSO. And already in 1960, Bushy defined Bushy automata for MSO, but they're non-deterministic. And people are trying to say, can we come up with a deterministic model for automata on infinite worlds? And the first attempt was, well, subset construction should work. And in fact, in 1965, David Muller published a paper with subset construction, which I showed you earlier, does not work. And it became clear that if we want to have a chance, in fact, we know that Bushy automata are not closed under determinization. We had this language, the language that says, from some point on, you see only one. That language has non-deterministic Bushy automata. So an attempt was to try to define a more general acceptance condition. And this people have played over the years with different notions. And the final notion that came is a very strange notion. When you see it for the first time, you say, what the heck? How do you come up with such a weird notion? And the only good explanation is you had to be there. Okay? Just emergent has, it's a good acceptance condition, but it takes a while to understand it. But let me define it. What is the acceptance condition? So we have a coloring, which is a mapping from S to some set k minus 1. You have a coloring, you have a k color. Okay? You have a coloring function. So now when you look at every infinite run, some colors appears infinitely often, some colors appear only finitely often. We are interested in, we said the priority of a run is going to be the minimize over the colors, the minimal color such that the set of points R of j equal, not R, C of R of j equal I is infinite. This is the minimal color that repeats infinitely often. Okay? So it's this coloring function that you put as your acceptance condition. And the requirement is that the priority of R has to be even. So there are, again, there are finitely many colors. One color, the colors are ordered. One color will appear infinitely often. And because one color will appear infinitely often, there is a minimal one, and that minimal one should be even. What's nice about this, if you want to, for example, to complement, then to reject, it means that the minimal color repeating often is odd, and you can do very simply, you do some kind of shifting of the priorities, and therefore this acceptance condition is naturally closed under complementation, which was, for example, not the case with Bushy automaton. If you take the deterministic Bushy automaton and you complement them, it doesn't immediately give you a deterministic automaton for the complement. You can do it, but it takes more work. So this became known as parity automaton. And parity, because we are interested in the parity of the priority, is it even or odd? So how do we use it? How do we use it now to do synthesis? So first of all, we need to be able to translate from NBW. We need the translation from NBW to DPW. Non-deterministic Bushy automata on words to deterministic parity automata on words. And parity automata emerged only in the, first of all, in the around in the late 80s. People used other conditions at the time. And the history of determinization was, I told you, in 1965 there was this false attempt. But in 1966, McNaughton published a paper with a correct determinization construction. What was the complexity of that construction? No analysis. 66, who cares? Only in the 80s we start doing an analysis of the problem, and we realized it was doubly exponential. In fact, I remember as I meeting McNaughton in a conference, I asked him, does he know what's the blow-up of his construction? Oh, he said, lots and lots of state. So if you take lots as exponential, then lots and lots is doubly exponential. So I guess he was right. He kind of intuitively knew. He said lots and lots of state. So in the by the mid-80s, became clear that even though the problem was nominally solved 20 years before that, now we have an open problem, which was, can you do it in one exponential? And that was done by Safra in the late 80s, become known as Safra's construction. It's not a clean exponential. Again, it's this 2 to the n log n, which we have seen before comes up when you deal with automata on finite worlds. So by the late 80s, we have this translation from NBW to DPW, which is essentially exponential. Okay, you can say this is close enough. This is exponential, close enough to exponential. I mean that when people use exponential, there are really two semantics. One is you have to have 2 to the Cn, and the other one you have 2 to the poly of n. There's some ambiguity. So this is, we'll call it exponential. So now there remain the small problems. The small problem, now we saw how to solve DFA games. We saw how to solve safety games, which we saw as really the dual of reachability games, essentially. But now we have a more general thing. These are games on infinite. These are infinite games, finite number of states, but the game has infinitely many rounds, and the acceptance condition is the parity condition. And this becomes known as the parity game problem. So this problem in some sense emerges, and this problem comes up in other areas. This is not the only place where it comes. If you know something like if you do mu calculus model checking, again it's equivalent to solving parity games. This problem somehow emerges around maybe 1990 or late 80s, around that period, and it's still an open problem. And the question is it in polynomial times? And there have been many papers, both on either analyzing the complexity, trying to devise algorithm with the best known worst case complexity, trying to actually build tools and check them to see that they perform well. So on both the theoretical side in terms of worst case complexity. So the initial algorithms for this were of the form of n to the k, where k is the number of colors. So, and then people start to do, can you do it with below k? So k over 2 or k over 3. And the last breakthrough in this saga, and this is still open, we still don't know whether it's in polynomial time. We know that it's not NP complete because we know that the problem is in NP intersect co-NP. So if this is NP complete, then lots of things collapse, so this is very unlikely to be the case. And so we think it's in polynomial time, we don't know. And the latest result just basically a month ago, right? When did the paper appear? But a month ago in stock, it's in quasi-P, okay? So what is quasi-P? Quasi-P is when you have n to the polylog. Okay. So you don't have a fixed exponent. It's a polynomial in the logarithm. So this is quasi-polynomial time. Of course, if you think of this, this can be horrible complexity for large n. But it kind of gives us an indication. People say maybe it's an indication that the problem is in polynomial time. And that, well, you know, there's nothing complete for quasi-polynomial time. So it would be it would be a major result to prove that the natural polynomials are complete somehow for quasi-polynomial time. It's not a complexity class that it's a very fragile class because you can only do. You have to be very careful. Your reduction have to be, I think, only like linear time reduction. There's nothing known. We don't have any problem. Nothing is known about it. So either, I mean, there are two possibilities. Either everything, there are very few problems that are natural problems that are there. This now, graph isomorphism. Generally, people think generally everything that's in P intersect one P should fall down to P. Okay? So they view it as an indication, but I said it's conceivable that some theory will show no, the problems are really somehow complete for quasi-polynomial time, they're not in polynomial time. But that also will be a major result. Either way, this will be a major result.
So if you just try to define it with Turing machines, that I mean, is not complete. You say
with nothing complete for these classes.
Even the halting problem for a Turing machine that runs over, n to the log n steps, something like that.
Part of the problem is that there are all kind of, if you have to remember, Turing machines are typically only robust up to polynomial because you can change all kind of result. The nice thing about polynomial time is that it's a robust notion. You can change the instruction set, you can go different machine. So it's robust under polynomial factor. P time is robust under polynomial factors. But for example, there is a result that separates non-deterministic linear time for deterministic linear time. But these are very, very fragile results because you have to have very limited reduction. And again, these models become very non-robust. The thing that we know, for example, right now when it's a polynomial time, and people say, I don't use Turing machine, I use x86, I say, it doesn't matter. All the relationships are always polynomial. You can translate between any two models. You have one tape, you have two tapes, all this reduction, you know, so why should you have one tape, for example? Okay, it's only reasonable when we said it doesn't matter, because all the kind of reduction from having, for example, two-dimensional tape to one tape, and all these reductions are robust up to polynomial. But as soon as you are not there, you lose this robustness. This becomes much more difficult to do complexity theory. That's why we really don't have interesting complexity theory around these other classes, because they're so much more fragile. No, it will not be robust, because it could be by itself a polynomial blow-up. So this is, as I said, this is really the kind of the latest result, and the quest to have synthesis for LTL, it's still very much an active research area. There are papers are still coming up. I said they are both on the theoretical side, you see progress like on parity game. On the practical side, people build tools, argue my tool is better than your tools, and things like that. So this is very much the frontier of research, and that's a good place to stop. Thank you very much. Any questions about today's lecture, about the whole series of lectures, about life, the universe, and everything?
Sorry, if I can. Just there's been a huge amount of work as well, right, on this kind of translation of non-deterministic.
This is still, I would say, an active area of research. In the sense, both on the complexity side, we kind of know it's n to the you know, 2 to the n log n, which is n to the n. We have lower bounds, so we know that this is the best. But you can still look at different construction, and you ask, you know, how natural and how elegant they are, how easy they are to implement. And the part of the problem is that if you look at subsequent construction is very much almost logic. To take all successors, okay? This is very much a logical operation. So it's very easy to implement it symbolically, for example. You want to reason about automata symbolically, no problem. Do subconstruction, it's very easy to implement symbolically. I mean, image operation is something that symbolic model checking does. When you look, for example, take a Safra's construction, I call it, it's a horticulturalist construction. In the sense, the state is some kind of a tree. And how do you make a transition? Well, take this tree, plant this subtree, prune these trees, move these trees to the right. I mean, it's well defined, and you can reason and you can argue about it. But one of the things, it's very, very hard to reason about it symbolically. So we only basically have explicit set algorithms there. And if you don't have symbolic algorithm, it just very much limited your scalability. So people take, and this they blow up so quickly. I mean, think about it, the point about n to the n versus 2 to the n, okay? Take n equal 10. Start with a formula, start with 10 state automaton. 10 state non-music automaton, not very big, right? 2 to the n is 1,000, okay? N to the n, 10 trillion, okay? 10 billion. It just, and people have shown it. They've shown that you start with very small, with like 10 states, and you end up with huge number of states. And because you have to do explicit states, so I think people have shown that there are some fairly small example where you apply self-construction, you end up with million state automatons. Start from 10 states, and you end up with million states. And because you have to do everything explicitly, I mean, it just really does not scale very well. So how to, you know, in some sense, this is very much whether this thing will ever be realized. It's very much up for, still I would say it's very much a research topic. The other thing that people realize is that this idea that you can sit down and imagine a system and write down exactly how it will operate, it's just very unrealistic. When people start to build a system, they really don't know exactly what they want. And so in fact, in part of this idea, it was called in software engineering the waterfall model. You start with specification, blah, blah, it goes down, you do this, blah, blah, it goes this. And this is very idealistic, and people now understand that it's not a realistic model for software development. And in fact, there was even a counter movement to that. What's the opposite of the waterfall model? Anybody know the lead software engineering? Agile, okay? Oh, just they have a general idea what you want. Just go and quickly cobble up something and go and show it to the user and get the reaction. And they will say, oh, no, I never thought about it. I don't want this to happen. There is a new requirement. Yeah, I told you yesterday that I want this. I don't really want this. And so kind of it's much more about kind of things, the moving target. And then the question is, can we, the problem is, can I have somehow a list of properties, and I should be able to very easily modify, drop one, add one, change something, weaken, strengthen. And so people talk about incremental synthesis. But this is still, again, very much research in moving target. Yes?
So what can you say about, so like, say you don't have like a hard constraint that you want, but you want like some sort of parsimony or something. Like, for instance, with your print driver, it could just, you turn it on, it decides to print everything continually, and like this will satisfy your requirements, but it is presumably not what you like.
So this is, again, very much a kind of active area of research. This idea that also in optimization, people talk about hard constraints and soft constraints. And hard constraints are the things that this should never happen, right? The engine should never blow up. But on the other, some of them are, well, they would be nice to have. And in particular, one thing that did not talk to you at all, some of the things may have to do with, to say, everything so far here was Boolean, either true or false, okay? But if I ask you, how much do you like strawberries in cream, you can say, if I ask you, do you like it, you might say yes. But how much do you like it? You say, well, I actually prefer blueberries. I don't dislike strawberries. Things are more refined. And so this is true. The requirements may not just be absolute. This is this, and that's it. Just 0 or 1. It could be quantitative. It could be in order in preference. So this is somewhat a naive. The idea is that it's very much a logic picture, very classical logic, right? Everything is there, just 0 and 1, true and false. And in reality, things in life are more complicated. And the question is, can we enrich the theory so that the whole theory of quantitative verification that you not get into, and quantitative synthesis where you try to have more than just 0 and 1. Okay, time for a break. Thank you very much. You've been a great audience.